Okay, we are going to finish off this DOE 1 stuff today. This is where we're at. Okay, so this is class time. So now we are starting off with finishing DOE 1. We left off here with the idea of replicates and repeat runs. Remember, we had that sad story of Wai Peng where he was running his reactor. It was a packed bed reactor. He was spiking mercury to some gas stream here. He had an online analyzer there, and he set his experiment, brought the reactor up to temperature, measured the concentration of mercury coming out, and he set the mercury concentration at one time, let it get to steady state, and then monitoring the concentration versus time of mercury. I've got something like this. That's where the reaction happens. And the problem was that he took each one of these data points. This machine samples, say, once a second or more. He took all those data points and said n was something like 1,000. And used that to calculate his confidence intervals. And we said that was wrong, right? We thought that was wrong. So, it is true he did have 1,000 data points there. But when he presented his results and said, all right, this particular catalyst will produce this conversion of mercury under these conditions, he got these really, really tiny confidence intervals because he included 1,000 data points, right? Okay, so what was wrong with that is that his 1,000 data points didn't really correspond to the true level of noise in his experiment. So let me clear that up. So his 1,000 data points were, we would say, repeat measurements. But they were not true experimental replicates. So what noise? There was some noise that he captured in these 1,000 data points, but that noise was due to what? Mostly. Yes. The noise he captured in those 1,000 data points was the noise associated with measuring that stream in his analytical device. But practically speaking, there is a lot of noise in his experimental setup. So for example, every time you load your catalyst in there, do you get the exact same amount of catalyst every time? No. The variation in the amount of catalyst that you have around the mean, there's some noise associated with that. When you heat your catalyst up to a certain temperature, you might not get to exactly the same temperature every time. And very importantly, when you're trying to spike the carrier gas with the mercury concentration, that is certainly not going to be the same every time. And in fact, that's probably going to be drifting throughout the experiment. When you set your gas flow rate, which will impact the residence time of your reactor, that's not going to be exactly the same every time as well, right? So a true replicate would include, I would say all of these things. So that would mean a true replicate would be, you would have to, this would be one run, then you'd reload with fresh catalyst. You probably have to do some conditioning, also maybe oxidize, reduce it to get it ready. Set the temperature, get your mercury into the feed stream, let it come to steady state, and take another data point. Set the flow rate, obviously, all those sorts of things. There's a sigma associated with all those things. And what we want in our repeat measurements is to capture all those sigmas into our replicates. Every time we do an experiment over, it should include all those noise sources. Does that make sense? Does it make sense how that was different than his repeat measurement that only included the noise of the analytical device? But you can go crazy with this too, right? You could think how far back do we go? What about the gas bottles that we're using? Are they as secure as, say, another shipment of gas bottles? Does that mean a replicate we have to contact our supplier, get another gas cylinder and hook it up and include that noise level? Or are different suppliers have different noise levels? Should we get from a different supplier? There's same with mercury. Should we order more mercury from different suppliers each time and set this up? You can go back and make your experiment unwieldy with the sources of noise that you're including. So there's obviously some judgment that you have to invoke here, and so whatever you do in your replicate, what you should do is when you're writing up your report or your analysis, you should at least explain what you mean by a replicate. This is what you did. Right? We set our flow rate values back to 0, and then we turned them up again. We restarted the mercury. We repacked the bed with fresh catalyst. All that sort of stuff. You need to explain to whomever is reading your report that this is what you mean by a replicate. So on the one side, no one would ever accept repeat measurements of your analytical device as any sort of replicate. And then on the other side, you can go too far. I've never seen anyone go too far on the side of doing too much for replicates. As long as you're communicating what you're doing and you are thinking, what are the major sources of noise in my experiment, and those better be captured in what I'm calling a replicate. Does that make sense? Okay. And there's some general rules of thumb that you can find out there for just good experimental procedure for that. Last thing in this DOE 1 is something we talked about before, is we want to make sure we design our experiments. So essentially we want to take enough data points so that if an effect is this big, our experiment has a power of, say, 80 or 90% of detecting the effect that is this big, if that's what we're after. Okay, so we don't want to overdo it with a bunch of experiments and find a bunch of small effects that aren't going to impact the bottom line, and we don't want to underdo it and only look for giant things that are either so obvious we already know them, which is probably the case. All right, any questions on those couple things? Okay, so now this DOE 1 was just getting you an idea of, all right, this is what is important in experimentation is kind of this really overarching general view. Now we're going to get into how do we do this as efficiently as possible. All right, so I'll start in your notes. So this is the DOE 2 notes, which everyone should have today. So how do we do this? How do we get experiments in an efficient manner? So we said before, we are in our nomenclature. Y was our response variable. That's the thing we're trying to optimize. And to do that, we're testing a bunch of x's. And so in our reaction example, we had temperature, pressure, concentration, those sorts of things. And we're wondering, how do those factors, those x's, impact the thing we're trying to optimize our response y? Okay, so when we're designing experiments, we need to know how many data points. And so let's just think of, if we're just looking at one of these values, let's say temperature. Now we're saying, okay, how does temperature impact the reaction rate or selectivity or whatever we're interested in there? And you could say, well, I could take run this reaction at a low temperature, measure the reaction rate. Then I could run it at a little higher temperature, measure that reaction rate, and I could keep going with that. And I've got a nice line there that has almost no noise, and I can draw a line through it. And I could do that with pressure. We talked about one at a time, experimentation not being that great. But I'm not talking about one at a time experiment right now. What I'm talking about is how many data points I've taken. So data points cost money, and out in industry they generally cost a lot of money. So a lot of people's time, a lot of resources to crank out a data point in general. So if this underlying relationship is linear like I've drawn it, I could have gotten that equation of a line with less than 1, 2, 3, 4, less than 6 points. How many points, what's the minimum number of points that I would need to draw a line? 2. So it would have been a little bit better if I would have taken the 2 endpoints. I circled those. Anyone see why I circled those and I didn't say, all right, I'm going to take 2 points right here? Which 2 points would give you a line you'd be more sure of? Probably the, pardon? The ones that are real spaced out. Think these have noise in them, right? So if they have the same level of noise, if you take points real close together and there's noise, this line can really move. If they're spaced out, that line is going to stay put better. Does that make sense? So that's one thing that we're going to try to do. We're going to try to spread out our x's as much as we possibly can. We're going to try to take data points at kind of the extremes of our region, and that way we're going to get better, more reliable fit of our models. So if we take 2 data points, we can draw that line, but we miss a bit something, right? If we only take 2 data points, we don't know it's a line, right? Before, we could be pretty sure that this was a linear relationship. If we only take 2 data points, we're not really sure. So we would need to test that assumption, and we'll do that later. But right now, in this stage of development, what we're going to do, again, we're trying to get this as efficiently as possible. We're going to say, let's first assume we just have linear relationships. We'll take data at the high and low value of all of our x's, and then later we'll come back and we'll test what's going on in between there to see, is that relationship really linear or not? If it's linear, we're done, and we're happy that we only took 2 points because we saved a lot of money. If it's not linear, then we've got to add some more experiments and try to model, what's happening in between there. Does that make sense? So we're going to start so when I say 2 data points at a low temperature and a high temperature, we say they are 2 levels, right? That's what the 2 level means. So x1, we set it at its low value, then we set x1 at its high value, and we find some y value there, some number for y. We are also going to code these levels again. So the temperature, the low value temperature, let's say it was 20 degrees, we would code that as -1, and the high value of temperature, let's say it was 100 degrees Celsius, we will code it as +1. So we're going to use coded values for these factors. You'll see the utility in that later. So now that was one factor. Let's say we had temperature, and what did we say? 20 degrees and 100 degrees. And let's say we had pressure, gas phase reaction, and let's say we did 1 atmosphere and 5 atmospheres. So these would be the low values, and these would be the high values. And again, these are factors. Our x values. So when we run, when we run a temperature of 20 degrees and 1 atmosphere, we get a y value. We run at another condition, we get another y value, and those are the reaction rate, the thing that we're trying to optimize. So the experiments that we're going to do then are, if you think of this situation, we have two factors, two levels. There are 4 possible variations between the 2 levels of temperature and pressure, right? I've listed 2 of those. So we can do 20 degrees and 1 atmosphere. We can do 20 degrees and 5 atmospheres, 100 degrees and 1, 100 degrees and 5. Right? 4 possibilities. You can actually figure that out, why they are called, sometimes they're called 2 to the k designs. When k is the number of factors, in this case 2, 2 squared is 4 runs. If we had 3 factors, all possible combinations of 3 factors, low and high, would be 2 to the 3rd, or 8 runs, and so on. So they're called 2 to the k designs. So this is what a 2 squared design looks like. Again, 2 squared, we have 4 runs, and these minuses are, I just left the 1s off. That is pretty common. So we have 4 data points, and we're going to get a number. For each of these is an experiment. Does everyone see that? So if this was temperature, if this was pressure, in our case we said that was 20 degrees and that was 1 atmosphere. We set our reaction at those conditions, we measure our reaction rate, and we get a number for it. That's an experiment. Okay, is any questions of what this means? It's very important to not get lost in some of the spreadsheet manipulations we do, and don't get lost between that and what's actually happening in the lab, right? The experiment that's being performed. That's pretty critical. So this figure right here just shows graphically what we call the parameter space. That's where we took data. So again, this was x1, this is x2. There's where we took data, under those values of temperature and pressure. And so we measured some reaction rate at each of those spots right there. Does everyone see that? Questions about that? So then the model that we develop is only good in this space. We're never going to try to extrapolate that. So that's why it's important to get a visual idea of, I took data in this region, because we're never going to want to take our model and predict stuff out here. So in general, you should be very nervous about extrapolating any sort of empirical model that you build. Empirical means we built it on data. All right, any questions on that? All right, this goes up 1 level. So now this would be a 2 to the 3rd design, and we have 3 factors. So this could be temperature, pressure, and this might be concentration of something. 2 to 3 is 8 runs. And this list is, you can prove it yourself, it's all possible combinations of high and low values for each factor. And keep in mind, in those 8 runs, for each of those, we're going to measure some number, some result for each of those. And then we add another dimension here. We had x1, x2, and there's x3. And now that cube represents the region over which we took data. And generally, when you see this reported in these circles, they will put the y values instead of the number of the experiment. So, questions about that? Let's look at this example. So we did a similar type of experiment where they had temperature, concentration, and catalyst. So these are the factors. x1, x2, x3. And yield was our response. So let's think about, we're not given the values, or I didn't bother to write them down, but -1 would correspond to some low temperature, +1 some high temperature. Generally the extremes over where we think it's reasonable to run safety-wise and the reaction actually occurs. We have concentration. This would be a quantitative variable, so some number for concentration here, high. Catalyst, it's a little hard to think of a low catalyst or high catalyst. It could have been that we were looking at a small amount of catalyst there and a large amount of catalyst, or it could have been what's called a categorical variable. It could have been two catalysts. It could be different catalysts, and we coded one as the low value, one as the high value. So let's just think of it that way. This was some catalyst, and this was another catalyst. We did 8 runs, and so we have that, what's called the cube plot. So here's temperature, x1. So low temperature, high temperature. There's concentration, x2. Catalyst is x through x3. That's front and back. So this data point would be low temperature, low concentration, and low catalyst amount. So that yield is 60. So let's see how those cube plots read. Okay, so what we should do now is, how would we analyze this data? My theory is that you have enough background where you can figure out the analysis of these 2 to the k designs. And so let's test that theory, shall we? How would we, if I asked you this question, on average, what's catalyst doing? What's the better catalyst? What would you say? So I'll sharpen that up. As we change from this catalyst, the -1, to the other catalyst, coded as +1, what's the average impact on yield? Give me a number. I'm asking for one number that describes the difference between this catalyst and that catalyst. And that's what you're going to put in here. Okay, work with people around you. Oh, work with Chris. Doesn't have notes. Any questions? Anybody got something? Pardon? So what number did you get? That's what I got. That's one way to do it. There's another way to do it. Another way to get the same exact answer. So think of, so you took the back face average minus the front face average. There's another way to think of it. So think of it. So that way is fine. But try to think of it another way. Yes, you get the same number. How you guys doing? Okay. So yeah, if you had this data, and I said, you know, here's one catalyst, here's another, and we're interested which one produces the higher yield. You know, how would you compare the yield of this one versus the yield of that one? That's one way of doing it. Did you get a number? Did you do that yet? Yes. Yep. How about you guys? Questions? Okay, does everyone have an answer? Okay, 1.5. Is that the answer? All right. Okay, just hearing people talk, they said, well, these data points here, I averaged those together, and then I averaged those together, and I took the average. So this will say y bar at x3 in its high situation, y bar where x3 was low. And you took the difference between those two and got 1.5. Did everybody do that, or did someone look at it differently? Ah, okay, good. I'm glad someone did it that way too. This way is fine. It works. It gives you this number, and very often we are going to be doing things this way. But now, when you did that, did you worry about the other things changing? When you averaged all these things together, did you worry about, now I got some stuff over here, temperature and concentration that were changing? Check. Okay, good. That's what I think John did too, which is good. Okay, good. That's what I was getting at with this question. So that's where what Jack is saying too. When you guys did this, did anyone wonder about that? How can we average these four things together? Remember, we say we only average things together that are the same thing, but we've got two other factors here that are changing. So another way to look at that, it does work out. So what you did is correct. But this is why it's correct. So another way to look at this data set would be when we go from 77 to 83. That was this run here and that run there, right? What's happening as we go from this run to this one to this one? Catalyst is changing, right? But temperature is the same and concentration is the same. Does everyone see that? So if I take the difference between these two data points, I have one estimate of what catalyst is doing, holding the other things constant. Okay, so what is that? 6. So this experiment would say, all right, yield, or rate yield in this case, reaction yield, increased 6% probably when I change catalyst. I've got another thing happening here, right? Same situation where catalyst has gone from, so that's this run and this run. And we compare that, those two things are the same, catalyst change. So again, between those two runs, temperature and concentration is constant, and we only change catalyst amount. And this time, if we compare catalyst at the high versus low, it went down by 3%. Okay. So there, what do we have there? 17. and minus 14. Okay, if you average those four things together, so we have four estimates of changing catalyst high to low and holding everything constant. So one good way to think about this would be, if I'm saying the effect of the catalyst, I would say it's 83 minus 77 is one estimate, plus 57 minus 60, plus 45 minus 59, plus 85 minus 68. I have four estimates of the catalyst effect. We're going to call it that from here on out. When I say catalyst effect, it means when I change catalyst, from its low value to its high value, what's its impact on the response? Why? And on average, yield went up 1.5. Does that make sense? Any questions on that? So if you're going to recommend a catalyst, tell us. Great question. Why should we think about it this way versus the other way? I think this gives us a little bit more understanding what's happening. The other way, we had a question of what are the other two factors doing. This way it shows those other two factors, if we pair up these values, don't change in those pairs. It also shows that in these 8 runs, we have 4 estimates of the X3 effect, right? So those are replicates for us, really. We have 4 estimates of what X3 is doing. So now, the final way that it's nice to do it this way is that the end of the story? Is the full sum of the story that you want to communicate to your boss that this catalyst is about 1.5 better than this catalyst? Or is there something else happening? What do you see, Abe? Higher temperature is better. Does everyone see that? That there is more going on here, that when we're at a higher temperature, catalyst 1 is the winner. When we're at a lower temperature, catalyst minus 1 is the winner, right? Does everyone see that? That's called an interaction. Write that down. We're going to see that guy a lot. So we would say there's an interaction between catalyst and temperature, probably. I think we have 2 data points. We have two estimates at the high temperature and 2 at the low. You could think about averaging these 2 minus the average of those 2. If I say it's better at the high temperature, that means it's better. The high temperature is better than the low temperature, in which case you're comparing these and these. And you have 2 estimates of the X3 effect at high temperature and 2 estimates of the X3 effect at low temperature. What's that? Okay. All right, we got it. So now there's we'll say there's an interaction between catalyst and temperature. So let's set aside the interaction stuff, and let's just ask these other questions. Find out what the average effect of concentration and temperature is. So do the same thing that we just did here, but let's do it for temperature now. So on average, when we increase temperature, what happens to the response? What happens to yield? So let's try to get one number for that. I'd like to write on this a little bit more, so I'm going to go over here. So we're doing temperature now. So the average effect of temperature is something. If you haven't done it this way, please do it this way. Please think about it, at least for now, in this situation. There we have 4 estimates of going from a low temperature to a high temperature, and we're holding the other factors constant in this situation. So take those 4 estimates of the temperature effects and average them together. Anybody get a number? Looks like a lot of people did. What'd you get? 20.5? Anyone else get that? I haven't calculated this one. 23? 23. As we know, truth is determined by votes. Just kidding. But anyway, we'll see. All right, so this is what we have. Moved on me. Oh, well, close enough. So plus 17 plus 26 plus 9 plus 40. Did I do that right? Okay, those are the 4 estimates we averaged together. So the temperature seems to be doing more than catalyst, right? The average effect anyway. Do you see any interaction perhaps? Okay, that's something that could be true. It seems like what Jack's saying is those 2 back face guys are higher than the front face ones. So we would say that could be a temperature catalyst interaction. I'm going to put a question mark by it because, after I spell it right, it's not exactly clear. What about temperature concentration? Doesn't look like it, right? Does it? But do you see that at some point we're going to run into a fuzzy situation almost here where we say, is this temperature catalyst interaction real or not? Could this be explained by noise or not? Okay, we've got to answer that question, and I'm sure you're confident we will answer that question. We will dream up some statistical test to figure out, is that interaction significant or not? Same reasoning is we say the average difference in yield when we change temperature was 23. We have to say, can that be explained by noise or not? Okay, let's do concentration. It's worth really doing all these. So the average effect of changing concentration from its low value to its high value while keeping the other things constant. Anybody get a number? Still too early? 5? 5's the winner? -5. So -1, -12, -9, +2. All right, anything else? So concentration doesn't seem to be doing much, not compared to temperature anyway. Does it seem to interact with any of the other factors? Kind of hard to say, right? May not be. Right? Hard to say from noise. Okay, so what we've done is we figured out how everything that we've done when I said the average effect of this, this, and this, those are called main effects, which means they are the big picture of the average effect of temperature or concentration or catalyst on the yield. I just had something and I wanted to edit, slipped my mind. But keep in mind, let's circle back to that catalyst one. When we did that catalyst one, remember the main effect was real small. It was 1.5. But here we identified a significant interaction, right? And we said there's more to the story when we change catalyst. We said at the higher temperature, things were better. Okay, so one thing that we have to be real careful of, and we'll hit this again, is those are the main effects. But if we have a significant interaction, which we think we do here, then we can calculate this guy, but because it doesn't tell the complete story, we're not going to really hang our hat on this main effect. We're going to go a little deeper and say, well, yeah, on average, catalyst didn't seem to do something, but there's a lot more to the story. If you're at high temperature, catalyst 1's the winner. If you're at low temperature, catalyst -1's the winner. Right? So if you have a significant interaction, this main effect value can be misleading. In fact, it is misleading in this case. That 1.5, if I just told you that, you'd say, oh, okay, those two catalysts aren't doing much. They're not much different. When in fact, they really are different. They just depend on the other factors. It interacts with at least one other factor. Okay, so I think we got that together. And here I show you those are all the main effects. So those are the results, what you got. These are the main effects right here, temperature, concentration, catalyst, and then those interaction effects that we talked about before, we can put a number on those as well. We haven't figured out how to do that yet, but we can put a number on the interactions. That's of the same order, the same scale as the main effects. And you'll notice not only do we have two-way interactions, there is one three-way interaction. So now our job is to look at these numbers right here and say we can calculate all these effects, and we got to figure out which ones are real. And by real, we mean there is a signal that stands out from the noise. So my guess is this 23 is a real effect. My guess is when we look at the noise in the data in the experiment, we'll probably say 23 is real. It stands out from the noise, but we'll probably say this 1.5 could be explained simply by noise. Right? Again, the main effect of catalyst is 1.5. It's not 0, but we'll say that's not 0 because of noise. We could think of it as if I calculated a confidence interval about this thing, it would include 0. Or if I did an hypothesis test on this, I would not reject the null hypothesis. So to test if these things are real or not, we are going to do a hypothesis test, or many of them. And our hypothesis test is going to be, well, the mean of that effect is 0, and the alternate hypothesis is going to be it's not 0. So we need to figure out noise. We need to figure out what goes into an effect. Is it a mean? Is it a difference between two means? So we need to set up the hypothesis test and test each one of those. And the ones that we do reject the null hypothesis, we'll say those are real, and those are worth studying. Temperature really is doing something, and we need to be able to model it. Here's the thing that I forgot, and now it just came back. So notice when we calculated all these effects, the cool thing is for each effect, how many of the 8 data points did you use in the calculation of the effect? Of all of them. When you calculated the effect of x1, you used all of them. When you calculated the effect of x2, you used all of them. So for every estimate of our effect, we're using all of our data. So that's what makes this design so powerful, is we're using all of your data, all of your time. So in each one of these effects, all 8 data points are going into it. And we know the more data points you throw into a calculation, the more degrees of freedom you have, the more precision you have. So each of these effects was 4 estimates of the average effect that we averaged together. When you have a 2 to the 4th design, we have 16 runs. All 16 runs will go into calculation of every effect. And that happens because they are perfectly balanced like this. Right? So this is this perfect balance, and you can pick 2 points and say, all right, that's catalyst going from low to high, and all the others are constant. And you can do that for each of those. That's why they are set up that way. Any questions? So I can't really think of a Friday cliffhanger. We'll just have to maybe, this is a gift to you, we're just going to bask in the glory of the beauty of the Factorial design, how they're so balanced and they're so efficient. So this is one of those weekends I don't leave you with this pent-up tension, but a nice, relaxing release. All right, see you Monday.